Concentrated sulfuric acid reacts with alkenes, alcohols and sodium halides. So we're looking at different parts of the specification here. It says name the mechanism for the reaction between concentrated sulfuric and an alkene. Alkenes always react by electrophilic because the pi bond is an area of high electron density, is able to donate electrons to an electrophile. The electrophile accepts the pair of electrons, and then because it was unsaturated and it can become saturated, it's addition. And we've got to do the reaction with propene, so I like to always do my alkene reactions using this kind of starfish formula. So propene is a 3-carbon chain, so 1, 2, 3. That's the rest of this hydrogens. Now, the tricky bit is remembering how to draw sulfuric acid. So in sulfuric acid, the hydrogen is bonded to an oxygen that is then bonded to the sulfur, which has 2 double bonded oxygens and a single bonded OH. So our curly arrow goes from the pi bond to the delta plus hydrogen. Then we break the H bond and put the electrons onto the oxygen. And what I always like to do then is we are trying to show the major product. So I describe this as the alkene. The starfish does the box splits. So up in the air go the hands and out to the side go the legs. It's a starfish. So that's what was already there. We've broken the pi bond and spread them out. Now if we're going to draw the major product, we need to put the carbocation in the place that would be most stable. So the highest number of carbons attached, we can see that the left-hand carbon has only 1 carbon attached, but the right hand has 2. So we're going to put the plus on the right-hand carbon as secondary carbocation intermediate, which means that the hydrogen will be on the left. This is the correct carbocation intermediate. Then we've got the OSO2OH. Remember, when we broke that bond, we moved electrons onto that oxygen, so it becomes negative. And then our last curly arrow would be from the lone pair to the carbocation. And then we can draw out the major product. And there we have it. That is our structure. So draw the structure of the minor product. So remember when we went back to that step where I described that as the alkene had done the box split. So my propene has moved everything out of the way. The minor product would have the hydrogen on the more stable carbocation and then the OSO2OH, the rest of sulfuric acid, on the other side. Then it asks us to explain why the product that we've shown in 2.2 is the major product. So our major product is formed from a secondary carbocation intermediate which is more stable than the primary, which would be the alternative one, as 2 alkyl groups have a greater positive inductive effect than 1. So that secondary carbocation intermediate is more stable and they're therefore more likely to form at that point, that first step when the alkene opens up, much more likely to form the secondary carbocation. Now it says butan-2-ol, so remembering that that is like this with an alcohol group on number 2, forms a mixture of 3 isomeric alkenes. Now, if we think about that, the double bond, when the OH is lost and the H next door, we could either go to the 1, we could go to the 2. So why is it 3? So it says draw the skeletal formula of 3 isomeric alkenes. Well, first of all, I'm going to go to the left and I'm going to say, well, that is but1ene. But then if I go to the right, I get but2ene. Now the thing to realise is I'm thinking there's nowhere else to put it. I can't move the double bond. And a lot of students will try to draw the isomer methyl propene, but you just couldn't make that from butan-2-ol. You can't make butan-2-ol become proper. So what is it? It must be something about alkenes. And then we remember that alkenes can have E and Z. Now but1ene can't have E and Z because each carbon of the double bond doesn't have 2 different groups attached, but but2ene can. This one that we've drawn has got the methyl groups going off in opposite directions, so this is the E-but2ene. We could get the Z-but2ene where Z is on the same side, Z-but2ene, and we've got that there. Then the question continues. A byproduct of the reaction of butan-2-ol with concentrated sulfuric acid has the molecular formula C4H8O. Well, that's the formula of an aldehyde or a ketone. So butan-2-ol would likely make butanone. So this is saying that somehow the sulfuric acid has acted as an oxidizing agent, which we know it can do in its reactions with halides, so perhaps it can do it in alcohols as well. So butan-2-one is causing oxidation, so it's an oxidizing agent. If we want to separate a ketone from an alcohol, because alcohols have hydrogen bonding but ketones don't, then we'd use distillation because ketones will have a lower boiling point than alcohols. What happens when concentrated sulfuric acid reacts with sodium chloride? This is when in our group 7 notes we think, oh yeah, it acts as an acid and donates a proton to make those steamy white fumes of HCl. And its role is to be an acid, or if you want to be specific, a H+ donor. Then it says it reacts with solid sodium iodide to produce several products. We get black solid, that's iodine, a yellow solid, that's sulfur, a gas with the smell of bad eggs, that's H2S. If we got choking gas, that would be SO2, and steamy white fumes here would be HI. So our black solid was iodine, our yellow solid is sulfur, you can write S or S8, and our gas is H2S.